Oh, can you hear me, Andres?
Yes, I can hear you.
Okay, yep. Yeah, I just had some connectivity issue.
No worries.
Yeah.
I can see you now. Actually, okay, now I can see you. I will wait for a little while to say hi to Necmiye, and then I will
Okay.
go to
Oh, Andres, could you please make me as a host?
you're not the host. How do I make
Yeah.
you a host?
So you go to
Okay, yeah,
participants.
yeah, got it.
And yeah,
Change host.
yeah.
Are you a host now?
Um, I think so. Give me
You
a sec.
should be.
Yes.
Okay.
I'm also.
So whoever signs first becomes the host by default.
It's you and me. My Cornell account has the host privileges,
Ah,
but
I
this
see.
is the other website account.
Hey, Necmiye, how you doing?
Sorry, I am muted. Good. How are you?
Good to see you.
Good to see you too.
Thank you again for participating and accepting to give us a talk. Just wanted to stop by and say hi. I'm gonna be with the audience, which is in the YouTube. We stream, broadcasting this talk directly to YouTube. But I just thought to stop by and say hi.
Yeah, good to see you.
Looking forward to your talk.
Thanks. I will give
Nishan,
the same talk tomorrow at the control
yeah,
seminar.
I
Yeah.
saw the control seminar tomorrow. Yes,
Yeah.
yes.
Yeah.
Great. Thank you again. Nishant will take care of the rest.
Okay.
Looking forward to your talk. Bye bye.
Bye-bye.
Hello, Dr. Ozay. It's a pleasure
Hi.
to have you.
Nice to meet you too.
Yeah.
Could we check the screen sharing?
Yes, please.
Just okay, now I need to remember. So I'll try. Wait, something happened. Uh-oh. But it doesn't allow me to share it. I can share this, but I don't know it. Is this working fine?
I can't see anything actually. Could you give me a sec? I think it's visible on the stream. It's just me who's unable to see it. But, but yeah, it's clear now.
I can also check from the link that you shared it.
Yeah, yeah. Now it's clear.
Mhm. Okay, it looks fine. I think.
Yeah, we can start in about a minute. Just yeah.
Can I try one other thing?
Yeah, sure.
Let me see. I want to be able to see the. Mm, maybe it's gonna be complicated. Just used. I wanted to see the presenter view on my end, but
Okay, okay.
I probably need to connect to another screen to do that. Anyways, I will go with this.
Yeah, and if any questions pop up on the stream, like I'll let you know.
Okay.
Yeah, yeah. So you don't have to worry about it. Yeah, I think we can get started. I'll just give an intro and then we can take over after that.
Okay.
Hello, everyone. Welcome back to the DDLC seminar series organized by the IDS Lab at Cornell University. This is Nishant, and today's talk is about some fundamental limitations of learning for dynamics and control. And it's presented by Professor Necmiye Ozay. And uh, I'll give a little bio about Dr. Ozay. They did their PS in Booker T University and their MS in Pennsylvania State University, and then proceeded on to get a PhD in the Northeastern University. Then from 20 between 2010 and 2013, they were a control and dynamic systems postdoc scholar at Caltech, and then they joined the electrical engineering and computer science department at UMich, and then that was in fall 2013. And currently, they're the Shenluan Family Faculty Development Professor of ECE and Associate Professor of EECS and Robotics. And they're associated with a number of research groups in Michigan. And their primary interest in research is about dynamical systems, controls, optimization, and formal methods with applications to cyber physical systems, system identification, verification, validation, and autonomy. And they've received numerous awards. I'll just highlight a couple just to keep it brief. And so they've received several awards, including the IEEE CDC Best Student Paper Award in 2008 and Best Paper Award from the Journal of Nonlinear Analysis, Hybrid Systems for the year 2014-2016, and DARPA Young Faculty Award in 2014, an NSF Career Award, a NASA Earlier Career Faculty Award, and a DARPA Director's Fellowship in 2016, and many more awards. And they've served as reviewer, chair, and organized a number of conferences. And also, they've served on the editorial board of prestigious journals like Automatica. And without further ado, I'll let Dr. Ozay take on.
Okay. Thanks, Nishant and Andreas, for the invitation. So today I will talk about some fundamental limitations of learning for dynamics and control. So let me start with some outline. So I will start by talking a little bit about the role of learning in dynamics and control. So there are like very exciting developments in recent years. And in my group, we used them as well, and we got some exciting results. But there were some frustrations as well, and that led us to look into like, are there fundamental limitations in these things? And I will particularly focus on two lines of work on the technical part of the talk. These are joint work with the first one, my former PhD students, Xiang Liu and Eduardo Zontak. The second one, my current and former PhD students, Xiong Zhang, Xiang Liu, Zhu Du, and Mario Schneier. And we have a Muri project with Eduardo and Mario, and some of these results are a result of that project. Okay, so this is a typical control feedback loop. And your standard control feedback loop, you have a plant that you are trying to control. You want to design this controller, and you have some task and mission specifications. And many of the components in this feedback loop can be learned. So you can learn the plant model, that's system identification. You can learn the task specification, that's inverse optimal control or inverse reinforcement learning. You can learn the controller directly from data, that's maybe model-free learning. And not shown in the picture, there are perception estimation modules that you can learn them as well. And in the end, when we learn some of these components, we still want to ensure some system level safety and performance properties, even if we have the learning components in the loop. And we looked at different pieces in this picture, and I will show some highlights on some of the results. For example, in this result, we are learning a plant model. Plant here is this rope dynamics. The dynamics of the rope is very complicated, and we are collecting data and trying to learn this model. And we are trying to do some safe planning with this rope by avoiding red obstacles and steering the rope to a desired location. And here the controller is designed based on this learned dynamics, and we can give some guarantees on why our controller will achieve the desired task and it will be safe. Here's another example where we are trying to navigate through some obstacle area with some low resolution camera data. This is the camera data on the right. That's the only thing that we use for localization. And again, we want to avoid obstacles and reach a target position. Again, in this case, we are learning the perception module. We can characterize the amount of uncertainty this perception module induces. And we can, again, plan safely, and we can prove some properties on how safe these trajectories that we are planning with are. Here is another example where we are learning the specification. So in this case, we are collecting some data in an AR/VR environment where the robot is picking up some objects and delivering them to certain parts in the state space. One nice thing about learning a specification is that this is very transferable. If you are in a new environment, if your task doesn't change, or if you have a new robot, you can still plan with your learned task. And here we learn in the VR environment, and we are executing in the new environment the task that we learned. And we can implement this on a robot, and the robot delivers whatever it needs to deliver to different places. So in doing all of these, one thing that happens is that if you try to learn, you train your neural network. Sometimes it learns. Once you learn something, you try to do some validation experiments and try to sort of quantify the uncertainty in the learned model. And maybe you can do a verification and you can get some guarantees on the performance of overall loop. But there are many times where you try to learn and it doesn't work, and you don't know why. You don't know why, whether it didn't learn because you are doing something wrong, whether your hyperparameters are wrong, or whether there's something fundamentally wrong with what you are trying to learn. And it's very hard, for example, if something didn't work, you cannot write a paper and say, oh, this didn't work, because you want to, like, maybe you didn't do it right. This motivated us to look into fundamental limits. Can we prove things won't work, or it will take a long time to learn under certain conditions for some general class of systems or general class of problems? And we started looking into these fundamental limits based on some frustration on trying to learn things and not being able to learn in the end, and trying to understand the core reason of why it's sometimes hard to learn, hard or impossible to learn. So the first part of the talk would be on some fundamental limitations of learning linear immersions, and this has some relations to Koopman embeddings. And this paper got recently published in Automatica, and you can look at the paper for additional details as well. Okay. So what are linear immersions? So this is the idea behind Koopman-inspired methods as well. So you have a nonlinear system, x that equals fx. You want to find a transformation psi such that you lift your system to some space z by applying this psi to your x, and the dynamics of this z is linear. I am saying lifting because typically this z is higher dimensional than x, but it doesn't have to be. And if you can find this psi, you will have a linear system, and it's much easier to do learning of this linear system, learning A. And once you have the linear system, you can do prediction on your nonlinear system using properties of linear systems that we better understand. And in the control setting, you can possibly do control easier as well, though I won't talk about control that much. So what happens in practice is that you represent that psi with a neural network, and you try to learn the network weights. So you are trying to learn this psi together with this A matrix by using data from your nonlinear system. And one question you can ask is that, does such a psi always exist? And under what conditions this exists? So Koopman theory says if you go to infinite dimensions, things exist, but in practice, we are working with finite dimensions and you are working with neural networks. So does this exist? Okay. So the first observation is that does such a psi exist is not really a well-posed question. And I think it's important to ask good questions to find good answers. This is not a well-posed question because the answer is sure, it always exists. I can take a constant function. I can say psi is equal to c. Then the derivative of the constant function is just 0. I can pick my a to be 0. And I can find such a psi for any dynamics that you give me. But there's a problem with this type of psi because the dynamics that I am finding has no information about my underlying nonlinear dynamical system. So this is not really a useful existence result. And the reason is that when psi is not one-to-one, I cannot revert back and recover my x just by looking at c. So maybe a better question to ask is that we should look for one-to-one psis, and we should ask whether one-to-one psis exist or not, because this one-to-oneness will give us the ability to look at the z dynamics and go back to the x dynamics. Okay, so we refined our question a little bit. And let me show you an example. So imagine I have a one-dimensional system evolving on this real line. And this one-dimensional system has 3 equilibrium points denoted by this red dots. And my f of x is this function over here. So it's positive on the left-hand side. Then it becomes negative in between 2 equilibria and so on. And that induces some flow on the real line. These arrows are showing the flow lines. So the left equilibrium is attracting, the middle one is repulsive, the right one is attracting as well. Okay, so if you think about this, you can say, oh, this has multiple equilibrium isolated, and linear systems do not have such isolated equilibrium. Maybe that's sufficient to rule out the existence of such a one-to-one lifting psi. But one thing you can do is you can find a lifting. Here, the blue line is my psi of x. And in this two-dimensional lifted space, if my A matrix is rank deficient, then my A matrix will have this subspace of equilibrium. And if this subspace exactly intersects my lifting manifold in 3 parts, then I will achieve 3 isolated equilibria type of behavior here. So maybe this is still possible, but maybe we should look for rank deficient A matrices to be able to capture these type of behaviors. Okay, so let's look at this problem with the existence problem with a numerical example. Now I am writing down my dynamics explicitly. So this is the same type of dynamics where I have explicit 3 equilibrium point. And I will construct a psi for you for the system. So this is my dynamics. This is my lifting. I am lifting to a 2-dimensional space. And this lifting function is very complicated, but I will try to draw the lifting function. But this is a one-to-one lifting function. And this is what this lifting function does. So it takes this interval in between 2 equilibrium point and maps it to a infinite line parallel to your x-axis on your new dynamics. And it's like there are, you can imagine there are like 4 intervals here. It's mapping each of these intervals to infinite lines in 2-dimensional space. And it's taking the equilibria and mapping those equilibria to exactly these 3 points that lie on x equal to 0 line. And if you look at my linear dynamics here, this linear dynamics is rank deficient. So everything on this red line, the x-axis is an equilibrium of your linear system. Therefore, it satisfies the intuition that I showed earlier. So there's a lifted system where I have isolated equilibria for my original system, and this lifted linear system captures the dynamics exactly. And this weird numbers here is just to make sure the speed of the flow matches my nonlinear system. But now I get a very simple linear system that represents this complicated nonlinear system with 3 isolated equilibria. But one thing I would note about this lifting is that this is a discontinuous lifting. And there is some power in discontinuous liftings. And we will talk about that a little bit in the remaining part of the talk. Okay, so it is maybe possible to immerse a nonlinear system with multiple isolated equilibria into a linear system. If I am allowed to use discontinuous liftings, this is just an evidence that this is sometimes possible if I allow discontinuity. But in practice, I am learning psi using a neural network. And all the popular neural network activation functions, they are continuous. ReLU is continuous. Your hyperbolic tangent is continuous. Your sigmoid is continuous. So in practice, we are trying to learn a continuous psi. Maybe I should change my question a little bit to map it to practice. And what I would ask instead is that, can I find a psi that's one-to-one and continuous, such that I can achieve this lifting? So that's the question that I will ask, because that's what we are trying to do in practice, trying to learn these things with neural networks. Okay, so now I need some definitions to state the main results. the examples that I show was for equilibrium points, but I will be a bit more general and I will talk about omega limit sets. Given an initial state of my nonlinear system, an omega limit set corresponding to this initial state is the set of all points where there exists a sequence of times where my trajectory approaches to these points. So it could be equilibrium points, or it could be limit cycles, or those type of objects as well. And so this, I will be more general than just by looking at equilibrium points. I will look at multiple omega limit sets instead. I will also define pre-compactness of a trajectory. So a trajectory from starting from an initial state is pre-compact if its closure is compact. So you can imagine this is just a boundedness assumption on the trajectories. And we have some extensions for backward pre-compactness, meaning if you just reverse the time in your system, and if you make your system flow in reverse time, and if the trajectory is bounded in the reverse time, the trajectory will be backward pre-compact. What we want to avoid is that trajectories that come from infinity and go to infinity. So that will be something we will try to avoid. Then for an omega limit set, we will define its domain of attraction as all the points whose omega limit set is this omega limit set. So that's going to be the domain of attraction of an omega limit set. Okay. So these are, maybe if you have taken a course on dynamics, you might be familiar with these concepts. Okay, so here is my more refined question. We know linear systems do not possess more than one isolated omega limit sets. Can nonlinear systems with multiple isolated omega limit sets, you can read this as multiple isolated equilibrium if it makes it easier to think about for you. Can these nonlinear systems be immersed into linear systems via continuous and one-to-one methods? And this is the question that we are trying to answer in this talk. Okay, so any questions on the setting? Okay.
I don't see any questions in the chat yet. No.
Okay. Okay. So this is maybe one of the key definitions we have. A system has closed basins if the domain of attraction of all of its omega limit sets is closed. And one thing you can observe is that every linear system has closed basins. And here is just to give you some examples. Here is a two-dimensional linear system with an attracting equilibrium in the at the origin. And the domain of attraction of this equilibrium point is entire R2, and R2 is closed. Here is an unstable system where I have this repulsive point in equilibrium. The domain of attraction of this point is itself, and since it's a single point, it's closed. Here is another system where I have a stable manifold and unstable part. The domain of attraction of this equilibrium is the entire x-axis, and it's closed. And you can generalize this. Every linear system, it always has closed basins. And what we will show is that it will be hard to embed or immerse nonlinear systems with multiple equilibria to systems with closed basins. Okay, so here is the main result. Assume the domain of my system is connected and forward invariant, and suppose these three things hold. The first thing is my system can be immersed into a system with closed basins by a one-to-one and continuous psi. The trajectories of my system are pre-compact. You can also have backward or backward pre-compact here. And this omega is the, or W is the set of all omega limit sets of X, and this set of all omega limit sets of X is countable, then this W set can only have one element. What this means, in other words, is that if your psi is continuous and one-to-one, and if the trajectories of the system are pre-compact or backward pre-compact, and if F has countable but more than one omega limit set, then F cannot be immersed in a linear system. So this is just saying if your F has multiple omega limit sets, but not infinitely many, not uncountably many, then you cannot find a continuous and one-to-one mapping to immerse it into a linear system. So a few notes about this. These conditions are not only sufficient, but they are also necessary in a sense. And this is necessary in the following sense. If I relax some of these conditions, then a linear immersion might exist. We already saw that if I relax phi to be not one-to-one, there are trivial linear immersions. If I relax psi to be discontinuous, we already saw an example. We already saw an example where a one-to-one linear immersion exists. If there are trajectories that are neither pre-compact or backward pre-compact, meaning trajectories coming from infinity and going to infinity, there are examples in the literature where you have these linear immersions. And if F has uncountably many omega limit sets, it's easy to find examples. You can just have a linear system, and a linear system will be an example of this. A linear system with multiple, infinitely many, but uncountably infinitely many omega limit sets. It's trivially linear, so I can use the identity mapping and I can get this thing. So all of these things are, in a sense, necessary for the existence or non-existence of linear immersions. So what are implications on learning? Maybe this is the more interesting part. As I discussed earlier, if I am using a neural network with continuous activation functions, what our result shows that, and I will talk about it a little more, this neural network will tend to collapse all the omega limit sets into one. Since it's collapsing all these omega limit sets into one, it cannot be one-to-one, and it cannot be inverted to predict X. So this is one of the implications if you are trying to learn with a neural network. You can enforce one-to-oneness by playing with your network structure or the structure of the lifting function. And a typical way of doing it is the so-called superlinearizability, where instead of learning this psi altogether, you impose a structure on psi and you say the first part of my psi will be just the identity lifting, so I will have my states repeated. Then I will only learn this phi part with the neural network. This is trivially one-to-one because I already embedded my state in it, so I can just do a simple linear projection to get back my state. And if you try to do that, and if your neural network is trained, and if the neural network is giving you a perfect fit, then this neural network needs to be discontinuous to perfectly fit your data. Of course, it cannot be discontinuous, but it can lead to high Lipschitz constants for your neural network. And we know when you have high Lipschitz constants, this degrades the robustness of the neural network. It will both make learning a bit hard, and it will cause problems in terms of robustness. Okay, so let's see some examples to get intuition. So here is a one-dimensional system with two omega limit sets at 1 and -1. Here is my picture of the flows. And I can define a lifting for the system if I only consider the domain from -infinity to 1, so my domain only includes one of the omega limit sets or one of the equilibria, then this is a valid immersion on -infinity to 1. Because in this range, this system has only one omega limit sets. At the point that I include 1 in my domain, now I have 2 omega limit sets, and this lifting function that I defined is not defined anymore at 1, so this is not valid anymore. Here is another example that's kind of interesting in the following sense. So this is a 2D system. The omega limit sets of the system are the origin and the unit circle here. There's a limit cycle there. And this is a system that has an isolated limit cycle, and linear systems don't have isolated limit cycles. So the question is it just a topological property that we are exploiting? If it was so, it wouldn't be possible to lift an isolated limit cycle, a system with an isolated limit cycle, to a linear system, because linear systems don't have isolated limit cycle. But this system can be lifted into a linear system if I take out the origin, so that there's only one omega limit set, which is the limit cycle. And here is the lifting in that case. And again, if I include the origin, now there are 2 omega limit sets, and our theorem shows that there shouldn't be a lifting. And if you look at the lifting function that I define, it's undefined at 0. So this lifting function is no longer valid as soon as I added the extra omega limit set in the domain. Okay, so far what I stated was liftings that are valid in the entire domain. But if you are doing learning, you have finitely many samples, and you are learning a neural network that only fits finitely many samples. So what are some implications on learning? Although I defined some implications on learning earlier, it didn't take into account the finiteness of data in learning. Now I will try to generalize the result a little bit to the learning setting where you have a finite number of data. Okay, so formally, I will state the learning problem as follows. I am sampling a set of points XL in my domain of the nonlinear system. I am picking a sampling time tau, and I am integrating my system forward from this initial condition for tau amount of time, and I am getting XL plus 1. I have n samples, and this is my flow function. And in the end, the problem I am trying to solve is the following. I want to be able to represent the lifting of the x plus point as a linear flow from the lifting of my x point. And I want to find this phi and a so that I minimize this cost function. I can define the set of optima of this optimization problem. And this is the set of all interpolating functions for the data set. So it's the set of all psi that satisfies this. One thing I know is that because the constant function is already in the set, I can always achieve 0 objective function for this optimization problem, and 0 will be the optimal objective value. But there might be other psi's that are not trivially a constant function that still give me 0 objective function, and I am defining all possible interpolating functions that achieve this. Okay, as I said, this set is not empty because I know there are trivial functions in there. And if you want to eliminate trivial functions, what I am stating will still hold if you add extra conditions to this optimization problem. Because one thing I will try to show is that this set F star doesn't have certain elements. And if you add more constraints and remove elements in the set, it won't have those elements that I will tell you they won't exist. Okay. In this case, this is a more learning inspired version of our result. If the points that you sampled from your domain is dense, and if psi is a continuous function that can differentiate your omega limit sets, then if your sampling time is small enough, this psi cannot be an optimal. So this is saying any psi that you will learn that can differentiate omega limit sets, it won't be an optimal solution of this problem, so you won't be able to learn that. So you cannot learn any continuous function that can distinguish omega limit sets. Again, this implies that when we are learning, the neural network will have to pick these lifting functions that are not one-to-one, because it needs to collapse this omega limit sets on top of each other. Okay, so to conclude, what we have shown is that under mild conditions for nonlinear systems with multiple isolated omega limit sets, there are no linear immersions that are continuous and one-to-one. Even if you pick A to be low rank, you won't be able to achieve this. And as I said, the implications here are you either need discontinuity on your lifting function, or you need to lift with a single function to a hybrid structure. So there's some relation to hybrid control here. Maybe piecewise linear dynamics is a better objective to lift in. And based on that, we started thinking about some extensions of this work, especially when we also have control. Instead of trying to learn this global lifting, which rarely exists, we are trying to learn local liftings. And if this local neighborhood has only one omega limit sets, then these liftings exist. And we have some applications on this, on learning these liftings and doing some safe constraint reachability type problems. The other thing that we are looking at is that if I give you two approximate liftings, but not exact liftings, is there a way to say one lifting function is better than the other? And we have some work trying to define pre-order relations between lifting functions so that there's a principled way of comparing different lifting functions. So here is one example of using these local liftings for doing some inverted pendulum task. And we can show that compared to local linearizations, if you do these local liftings, you can get a much better and larger reachable set using a hybrid system with much fewer nodes. Okay, so this is a good point to maybe pause a little bit and ask if there are questions. If not, I will.
Yes, there is one question actually. The question is, I'm wondering whether a polynomial nonlinear system has a linear immersion or linear immersions.
So there are polynomial nonlinear systems that have linear immersions. There is some work, for example, by Rafael Jungers and Paulo Taboada on polyflow dynamics, where they show that there exists linear immersions for certain classes of polynomial systems. But those polynomial systems they have single omega limit set. So being polynomial is not the issue, having multiple omega limit sets is the issue. So if you have a polynomial system with a single omega limit set, then you might achieve a linear immersion with a continuous one-to-one mapping.
Thank you. There's another question from Andreas. And what if the system imposes some delays? Would there be any implications for the lifting function?
That's a good question. We haven't looked at delays per se. So when you start talking about delays, you are already in infinite dimensions, and everything that we are doing here is using the fact that you are moving between finite dimensions. I don't have that much of a intuition on what the effect of delays would be, but my initial sense is that it might break our proof techniques because we are really using the finiteness of the space that we are lifting. And if you start with an infinite dimensional system, things can break.
Yeah, I guess we can take one more question before we can. Yeah. So, could you elaborate a little bit why having psi x as a constant function facilitates obtaining always a linear system?
So let me maybe go back. So if psi x is the constant function c, now if you take the derivative of c, derivative of c is 0, then I can have a dynamics that looks like derivative of something is 0, so it will always remain constant. And it satisfies this property of lifting. So I started with an x, I lifted it to a constant, and x itself flows here, and this other system just stays at that constant forever. Although x flows, if I take x at a later time and lift it, I will still get the same constant. So if I apply this lifting function to the flowing x, I will always get a constant on the right-hand side. And my dynamics is 0, so the dynamics of the z dynamics is also constant. So this is matching this definition of obtaining a linear function such that when I apply the lifting at the initial point and a later point, I will get the same solution for the z part. But of course, it satisfies this definition, but it's not that useful because it doesn't tell me anything about the system that I am trying to learn. And if you look at this optimization problem, that system that I defined will give 0 objective value here as well, because it satisfies everything over here. So it's c minus c is 0. So it perfectly interpolates what I am trying to do, but it's not one-to-one, so it's not giving me information about my underlying dynamics. Okay, so maybe I will move on to the second part. And the first part was maybe an impossibility result. Now the second part will be a hardness result. And the question is, how do we measure hardness? In computer science, there are 2 ways of measuring hardness. One is computational complexity. This is related to how the computational cost of an algorithm depends on the input size. And I have worked back in the days on computational complexity of some learning problems where you are trying to do system identification for a hybrid system. So this is how complicated of an algorithm you need to solve a problem. The other measure of hardness is related to learning algorithms, and we will use the second measure of hardness, which is sample complexity. And sample complexity is roughly defined as how a performance metric of a learning algorithm depends on the number of samples or number of data points that you are using for learning. We want to understand this rate of the change in the performance based on sample size. And there could be multiple metrics. For example, if you are trying to do system identification, maybe the metric that you are looking at is your approximation error. If you are maybe doing control, the metric could be the regret of the controller that you are learning versus the best controller that exists that knows the actual system. And the metric that we will use in this work is probability of stabilizing. So we will try to find a controller. And in the end, we want the probability of this controller stabilizing my system to be high. So here is the setting we will look at. This is the sample complexity of a learning algorithm. Sample complexity of a problem is the complexity of the best algorithm. So similarly, both for computational complexity and sample complexity, you can talk about computational complexity and sample complexity of an algorithm. But we want to talk about complexity of a problem. And if you talk about the complexity of the problem, you want to figure out how well the best algorithm performs, or how fast the best algorithm computes in the first case. Okay, so here is the setup we will be interested in. We are given a discrete time linear system from some class Cn. So this linear system looks like this. There's an A-B matrix that we don't know. There's some noise affecting my dynamics. And I am observing the state trajectory X. I have a time budget N, and I have an input budget because I don't want to arbitrarily increase my signal to noise ratio. I have an input budget sigma U. Then given this time budget and input budget, I want to construct a learning algorithm pi that interacts with the system. Interacting with the system means picks these U's for n units of time, collect this data, and from that data, it outputs a controller k-hat. So it estimates a controller k-hat. And we want to know whether this k-hat stabilizes our unknown system or not. So there's an unknown system. There's this learning algorithm that interacts with unknown system for n units of time. And at the end of those n units of time, it outputs a controller k-hat. And we want this k-hat to be stabilizing with high probability. And there's no restriction on this pi. You can use your favorite algorithm. You can excite the system for n steps. Maybe do direct data-driven control. Maybe do reinforcement learning. You can excite the system and steps. You can do system identification and do certainty equivalent control. You can do more online active learning where you look at what you have seen so far and try to pick your next input in a smart way. And that's fair as well. And what we will show is that no matter what pi you use, this problem can be hard. And we will see what is the core reason for hardness. Okay, so here's our problem statement. Our algorithm outputs some k-hat, and we want to know the probability that when I close the loop with this k-hat, this system, closed loop system is stable. And we want to understand the worst case stabilizing probability. So there are lots of ABs in the system. Is there one that gives me the worst probability? And the sample complexity of the algorithm will be measured by this, where we want to understand if this worst case probability of stabilizing is larger than a given constant. And the thing that we want to understand is if I have a fixed probability of stabilizing, what is the number of samples n that I would need to achieve this fixed probability? What is the minimum number of samples that I would need so that with high probability I can stabilize? And we want to understand how this budget n, or number of samples that I need, scales with the system dimension. So if there exist algorithms that make the scale width linearly, maybe I am good. It's easy to learn. But if this n is scaling exponentially with the system dimension, then it will take me a long time to learn to stabilize if my system is high dimension. Okay, so how do we establish hardness? Here is our roadmap. We want to find a class of systems such that no matter what algorithm you pick, this achieving stability with high probability will require exponential amount of data and exponential in the system dimension. So here is the key insight. Any class, if it has a pair of systems that are hard to distinguish and hard to co-stabilize, then learning to stabilize will be hard. Why I need both conditions? If these systems are easy to distinguish, what I would do is I will learn the dynamics of my AB. I will do a SysID. If that's easy, I can do it efficiently with small amount of data. Then once I learn, I can design a controller for that specific system, and I will be done. If these systems are co-stabilizable means there exists a controller that stabilizes both, then I don't need to learn them precisely. I just need to learn some uncertain set of systems that I can co-stabilize. And without learning which system in that set I need, I can find a controller to stabilize every system in that set. So learning will be easy as well. But if things are both hard to distinguish and not co-stabilizable, then I will have trouble. And here is the sort of definitions of hard to distinguish. Two systems are hard to distinguish if, when driven by the same algorithm, the probability distribution over the state trajectories that they generate is similar. And not co-stabilizing means in this context, there does not exist a single K such that both of these matrices are stable. And here we construct two systems where you can imagine these systems are in discrete time, a first order system cascaded with delays. And these systems only differ in the first entry of their B matrix. And maybe the only thing, even if the only thing that you are trying to learn is this B1 entry, this is going to be hard to distinguish and hard to co-stabilize. This is hard to distinguish because the stabilizing controller, for a co-stabilizing controller to exist, you need this M to be exponentially close. So if this difference between 0 and M is fixed, then you won't be co-stabilizable very quickly because of this exponential dependence. So here is the formal theorem. Maybe it's a little complicated, but if you pick these M's carefully, then you can construct a pair of systems with parameterized with the dimension n, such that any learning algorithm will need exponential amount of data to be able to stabilize these two systems. And this is kind of the number of samples that you need. It's exponential in the dimension. Maybe this is what you should pay attention to. And it also depends on your signal to noise ratio. Of course, if you have higher signal to noise ratio, you can have a smaller number of samples and achieve something similar. Okay, so maybe let me try to quickly wrap up this part as well. Learning to stabilize a linear system is hard if we have systems that are hard to distinguish and hard to co-stabilize. And this generalizes to many other learning tasks. In general, learning to control a system is hard if the systems are hard to distinguish and the task is hard to achieve with a single controller. So this is a more broad idea that's applicable to all hardness of learning problems. Our results generalize some of the earlier work in several aspects, but there's one part that I kind of lied to you so far, so let me reveal this. I only showed you that learning to stabilize a linear system is hard if I am trying to learn a static linear state feedback controller. So your learning objective also changes the hardness. And one observation here is that although for stabilization, this linear state feedback controllers are a general universal class, they are not universal for co-stabilizing. So there are systems that are not co-stabilizable with a static linear feedback, but they are stabilizable with systems with feedback controllers that have memory and that have dynamics. So our current work is try to understand if we generalize the controller class, can we break this hardness result further? So that's something that we are looking at. Okay, with that I can conclude. I think learning is exciting, but we should be aware of these fundamental limits. Although these two results, in a sense, look negative results, in both cases, we obtained these results and they helped us to ask more interesting learning questions because we understood the limitation and we can say in the Koopman setting, oh, maybe we should look at discontinuities and hybrid structures. And in the linear system setting, we said, oh, maybe we should look into a richer class of controllers. So I think looking at these hardness and impossibility results are important so that we can develop better learning algorithms. And with that, I will stop and I can take more questions.
Thank you so much, Dr. Ozay. There's a question, I think it's a follow-up from a previous question. If a nonlinear system only has a stable Lyapunov equilibrium point, does it imply the existence of a linear immersion?
So this is a sort of very new result. So there's a classical result called Hartman-Grobman theorem, which says if the stable equilibrium is hyperbolic, meaning if you linearize around that stable equilibrium and if that linearization is stable, then there exists a linear immersion. You don't even need to lift. You can just morph the space, and in the same space, you can find linear dynamics. There's a very recent result by Eduardo Zontag and Matthew Kowalheim that generalizes this and removes the hyperbolicity assumption, where they show if you have I think if you have an asymptotically stable equilibrium point, you can always find a linearization in the region of attraction of that equilibrium point. And they use Lyapunov theory type ideas to prove the existence. This is like, the paper came out like last month or something.
Yeah, I think they're also convinced they say it is reasonable, yes. So, yeah. And before other questions pop up, like I just have this question. When it comes to probability of stability, like the conditions that you provided at the end, where you need so much data, an exponential amount of data to ensure that delta 1 minus delta stability. What mathematical framework have you guys used over that? Like, is it some concentration inequalities or some
So there are two things that's going on here. One thing you need to characterize. So there are two things you need to characterize. One thing you need to characterize is this amount of distinguishability. And amount of distinguishability, to characterize that, the mathematical tool that you use is you look at the trajectories generated by these systems under the same learning algorithm. These trajectories, there will be a probability distribution over these trajectories. and you need to measure the distance between these probability distributions between trajectories. In this specific setting, we were using KL divergence. There is something that pops up in that KL divergence that shows this thing is hard. The other thing is for the co-stabilizability part to figure out like how close this M should be to each other for finding stabilizing K. We use very standard like undergrad control tools to write down the closed loop sort of eigenvalues and checking those eigenvalues are less than equal to 0. So for this is just undergrad control and writing down the closed loop and such. But for here, we need KL divergence. One thing we recently did, it should pop up in archive. So we were thinking, this is more on the system identification side. Here we are considering Gaussian noise. We were thinking whether having bounded noise will simplify problems or not. When you have bounded noise, the thing that happens is that your trajectory distributions will have bounded support. Therefore, and the supports for different systems won't be the same. So KL divergence is not no longer well-defined. In those cases, we ended up defining using TV distance. It didn't break this complexity in N, but we found some interesting results that there's a difference between bounded noise and Gaussian noise when you are trying to learn the system, do the system identification, where you get something like from square root of t to t improvement if you are using bounded noise.
Thank you so much. Yeah, we have more questions in the chat now.
Okay.
Could you share generalization on what if the external input might change the structure? Example, the number of omega limit sets changed.
Can you
I
repeat?
can. Yes. Could you share generalization that what if the external inputs might change the structure? Example, the number of omega limit sets change.
That's a good question. So a few things there. Everything that I said, although this last part we looked into control as well, everything that I said here is for autonomous systems. There is no control input. When there's control input, things are a little trickier and harder in some senses and maybe easier in some senses. We don't have it written up, but one of the hardness is like, how do you define a system that's nonlinear with an input? Because our typical definition is like every system is nonlinear. It's just that some of them are linear. With a proper definition of a system that's nonlinear, a system with an input that's nonlinear, we have a result that shows that you can never get a system that's linear with a lifting. But that all depends on how you define this nonlinearity. So short answer, things get more complicated when you have inputs, even how you define what is linear and what is nonlinear. But I think the question is for a fixed input, maybe constant inputs, but maybe different constant inputs. There are different number of omega limit sets. Yeah, I think things with, even in the Koopman theory, I feel like things with inputs are less understood. So I don't have a good answer. But in general, I don't know of a very good positive result, even in the infinite dimensional case, with inputs.
Okay, thank you. And I think there's one last question that we can take. Could you give an example of two real-world systems that are not co-stabilizable and hard to distinguish?
So I think I think this is not too far from a real life system in the sense that this is essentially saying take any one-dimensional dynamics, like this could be a single integrator dynamics, and have a lot of delay. And if there's a slight feed-through term in your input in one of those and no feed-through term in the other one, then you will get this type of behavior. So even like single integrator, lots of delay gets you in trouble.
Thank you so much. I think that's all the questions we have for today. Yeah.
Okay, thank you.
So, yeah, thank you for giving this talk. It was a pleasure listening to you.
Thanks. And thanks for the invitation again.
Yep.
Bye-bye.
Bye-bye. All right, everyone. See you next week. Bye-bye.